Right. Thank you very much, Chris, for the invitation and for the introduction. So let me spend a few minutes just introducing myself. And the next slide is the hardest one. I was really um, puzzled whether I should include it or not. So I grew up in Greece, and this is kind of like a footage that maybe I shouldn't be teasing you with sunny Greece in the middle of the winter, right? So, and we are surrounded by water, and it was inevitable for me growing up to develop this passion about, the ocean and boats and so forth. And this is one of the highlights. So winning like the Greek national sailing championships in 2013. But it, but it was inevitable for me to get into naval architecture and marine engineering. That's my undergraduate background. And there I realized that, and I was really fascinated realizing that, we can use computers and mathematics to explain what we see, to simulate fluid flow and solve Navier-Stokes equations and so forth. And that was my first experience ever with research. So I was running some spectral element, direct numerical simulations of flow past the cylinder, which is a deceptively simple yet very rich dynamical system with a lot of interesting behaviors like chaotic wakes and turbulence and so forth. So, and at that point, I was really a user of a code. Someone gave you a spectral element code, and I was playing with the parameters and producing results and so forth. And I got really interested. I didn't know how this thing worked. And that I applied to grad school, and I was really fortunate to be accepted by Brown. So I got to work with one of the godfathers of spectral elements, George Karniadakis, and actually learn how the methods work. So I spent a lot of time in my PhD working on high order methods and high performance computing. In particular, I did a lot of blood flow simulations in the human brain, so flow and fluid structure interactions. And towards the end of my PhD, that problem motivated a transition I made towards data-driven algorithms, a concept that I will introduce, namely multi-fidelity modeling and uncertainty quantification. And this multi-fidelity model framework turns out that it has a lot of applications in many different fields. And I'll show some results in data assimilation in the ocean, design optimization, and inverse problems. So this is just some figures and some highlights from my time at Brown. And then eventually I'm applying these data-driven methods these days as a postdoc at MIT, going back to engineering, for design optimization under uncertainty. Also, we have a project on an environmental study to devise a cost-effective sampling plan towards quantifying the anthropogenic effects of ocean acidification. And I'm working with a student. I'm supervising a student that is using deep learning methods for autonomous navigation of marine vehicles. And then the last bullet that came out as a side project, it was one of those late night eureka moments that we can use these machine learning methods to actually solve differential equations without ever discretizing the equation. And I'll talk a little bit about that later on. All right, so let's start with a motivating example. How did I switch from doing blood flow simulations to machine learning? So I was studying systems like that. So this is an arterial network consisting of the biggest arteries in our brain. And we were simulating fluid flow and fluid structure interactions to identify the stresses on the arterial wall in an aneurysm, hoping that we can provide some useful information to the doctors whether to intervene or not. And we have a collection of models we can use. We can use very high fidelity spectral element simulations. And this video shows that. And these are supercomputing simulations. So actually, this particular case was the finalist of the Gordon Bell Award in 2012, run on the Blue Gene machine in Argonne. But there are many choices we have to make. For example, there are many parameters that we don't know due to our modeling assumptions, or they're really hard to measure in practice. Say, for example, the elastic moduli of the arteries, the exact geometry. We are confined in simulating truncated arterial domains because we cannot really afford simulating the whole arterial tree, so we have to impose proper inflow and outflow boundary conditions. So, and this sometimes can be measured, other times cannot. So we have a lot of questions coming up. Also, we have simplified models, right? We have 3D models, we have 1D models, we have 0D models, empirical formulas, and so forth. So how can we construct a robust and predictive framework that can learn from heterogeneous information sources? That's one question. Then how can we use these surrogate models to perform predictions, but also quantify the uncertainty associated with these predictions? And then if our budget permits, how can we optimally acquire new data to enhance our knowledge about the system? And how can we scale this workflow to problems of realistic complexity? So today I'm going to introduce some tools that gives us one pathway to addressing those questions. And so one tool is Bayesian regression. And we're going to use I'm going to introduce Gaussian processes as a Bayesian regression tool. And I'm going to talk how we can use Bayesian, Gaussian processes to build a multi-fidelity, a probabilistic multi-fidelity modeling framework. Then building on top of that, I'm going to introduce the concept of multi-fidelity Bayesian optimization, and I will show you some examples how can this be used to solve efficiently any sort of parametric problem, like a design problem or an inverse problem where we have to repeatedly solve the forward governing equations many times. And this is just a sketch where we're going to try to calibrate the outflow boundary conditions in simulation of an idealized carotid artery. All right, so let's start with a very quick crash course on Gaussian processes. So Gaussian processes can be used as a non-parametric Bayesian model. So they can be used as a prior distribution over functions. And the reason we use Gaussian processes is not because anything in this world is Gaussian, but mainly they are, you can think of them as the linear algebra in a probabilistic world. So they have some very nice properties that allow us to build models and perform inferences. So the two very attractive properties are the marginalization property of the Gaussian process and also the conditioning. So the posterior of a Gaussian process conditioned on data will also be a Gaussian process. And there's some very well-known connections between deep neural networks that people are using these days in machine learning, kernel machines like support vector machines, and Gaussian processes. And for the students that are really interested in learning, there is a really great book by Carl Rasmussen called Gaussian Processes for Machine Learning, and it comes with MATLAB code, and it's a really, really good starting point for this type of tools. All right, so we're going to use Gaussian processes to solve nonlinear regression problems. And this is kind of like, we take a different approach than what we usually do in scientific computing, where we assume that our unknown function f can be represented as a linear combination of some bases that we choose, and we proceed by solving for the basis coefficient. Here we say, okay, we do not know f. We have some data, x and y. So we're going to put a Gaussian process prior on f. And then given the training set of observations, we're going to calibrate what they're called the Gaussian process hyperparameters. So these are the parameters that define, that they parameterize the mean function of the Gaussian process and the covariance kernel. So this is the modeling choice. We have to choose a mean function and a covariance kernel. So we're going to solve an optimization problem to calibrate to identify the optimal parameter theta. And once we have that, we can condition on all the data that we've seen to perform predictions. And this summarizes the sketch. We start from a Gaussian process prior. So each of those, if I sample the prior, I get continuous functions. And the choice of the covariance kernel governs the property of these functions. We'll talk about this later. Then we see data, we calibrate the parameters, and now we arrive to a posterior distribution. And these are just samples from the posterior, which, as you see, what happens here with the inference process just takes the Gaussian process and grabs a data point and just constrains the process around the data point that we have observed. And in between, we do have some variance, and this is kind of like a natural measure of uncertainty. So the model is pretty sure what happens around this point because we have observed, but there is some uncertainty associated with any prediction that we make here. And for example, we can use the mean of the Gaussian process, which is the blue line, to perform predictions, or we could use any other sort of moment to, depending on what we were trying to quantify. So when it comes to choosing covariant kernels, one can make some standard choices. And there's just different families, the Matern family, the squared exponential. They depend on parameters that quantify the length, the correlation length scale of the data. For example, the Matern kernel also have this parameter nu that controls the differentiability of the sample paths. So just by changing this parameter nu, which we actually learn through the optimization, we can get functions, we can model functions that are completely different in nature, like ranging from very rough paths like Brownian motion type to infinitely smooth functions. All right. And the nice thing about Gaussian processes is that inference is exact. It's very simple to code this up. This is the training step. We just have to maximize the likelihood of the data given the inputs and the model parameters. Of course, this has an unfavorable scaling because we have to invert this covariance matrix, which is dense, and so it scales cubically with a number of data, but there are ways around it to make it more efficient. And then we also have prediction because the conditional of a Gaussian process is Gaussian process. We have closed form expressions for the posterior distribution. So now the main catch here is someone has to be very careful about how on choosing the prior, and that happens with all Bayesian methods, right? So the choice of the prior encodes any prior knowledge we may have about the function. So if we know that our function is twice differentiable, we can use this information here. If we know our function is periodic or monotonic, we can use this information at this point. It also controls the smoothness of the sample paths, therefore the regularity of our predictor, the accuracy and the uncertainty. And then you see here, I have two different choices of priors, exactly the same data set, but the model we obtain is completely different. Also the predictions and also the uncertainty associated. And it also affects the conditioning of from a numerical perspective, the choice of the prior affects the conditioning of the covariance matrix, which we have to invert during model training, and therefore the efficiency of the algorithms. All right, so this is the main building block which I'm going to use throughout the rest of the talk. So let's introduce the concept of multi-fidelity modeling. Oh, before we say that, there's a very nice project in Cambridge. So one can naturally ask this question, so how am I supposed to choose a prior? Could this be automated, or do I really have to rely on human expertise on that? And the answer is, people are trying to say we can have automatic ways of doing that, and that's one effort in Cambridge, where they have all this dictionary of priors, and then during model training, they try to come up with combinations, the optimal combination of different priors that best explains this data. So this process of choosing the right prior distribution can also be automated. All right, so let's look a little bit about multi-fidelity modeling. So in the multi-fidelity setting, we have a collection of models, say model 1 to model S. Model 1 is very fast to compute, but the prediction that it returns, it's not accurate, right? You can think of it as a very simplified model of the complex system. And then model S will be our highest fidelity model. It's very expensive. Evaluating one point there could take 2 days on a supercomputer, but we trust it. So now the question is, how can we blend this information seamlessly to predict the quantity of interest? And this is a problem of statistical inference. So let me give you like a visual example of that. So let's assume that we have a one-dimensional function. The true function is this black curve that we don't know about, so we're going to put a Gaussian process prior on it. Then we have 4 points, 4 observations that were very expensive, but they're very accurate. They lie exactly on the function. And now, okay, we train a Gaussian process, and this is what the Gaussian process is going to give us. It's going to interpolate the 4 measurements, and then in between it gives you this big variance telling you, I'm quite uncertain. I don't know what's going on. I don't have enough information to pin down this function. All right, so that would be a single fidelity Gaussian process regression. Now assume that we have, in addition to those 4 points, exactly the same 4 points here, we have, in addition to that, access to a low fidelity model that returns those blue squares. So, on its own, this data is useless, right? It's totally inaccurate. It's way off the real function. But it does capture some trends. So it is correlated. This low fidelity model is correlated with a high fidelity function. So using this multi-fidelity framework of Gaussian processes, we can synthesize this information and come up with a predictor that gives you a pretty good answer. And as you see, the uncertainty has also has gone. All right, so let me show you how this is done with a little bit of math. So we're using an autoregressive model that was put forth by Kennedy and O'Hagan in the early 2000s. And pretty much we're modeling the response at the level of fidelity t as a Gaussian process, which is related to the response at the level of fidelity t minus 1. And so the levels of fidelity are ordered in increasing order. So t is high fidelity, t minus 1 is lower fidelity. So high fidelity is just a scaling of the lower fidelity plus some discrepancy terms. And we model ft minus 1, and delta t using Gaussian processes. And now this scaling quantifies how well these models are correlated. And this is something we learned when we jointly optimize over all the data. So we learn what this scaling is and whether there is any correlation or not. Again, using all the nice properties of the Gaussian processes, we have analytical formulas for the inference and the posterior. And the only thing that changes now, we have this covariance matrix K that corresponds, that's constructed, has a block structure, and each block corresponds to the contribution. So the diagonal blocks correspond to the contribution of each model, and the off-diagonal blocks model the cross-correlation between the different information sources. So as you can imagine, I already mentioned the cubic bottleneck scale of inverting K. If we have a lot of information sources, this matrix becomes quite large. But under some mild assumptions, we can decouple this problem, and this is some results by Legratier in his thesis 2014, where we can do some conditioning arguments and actually decouple this problem into S-independent Gaussian process regression problems, where S is the total number of information sources we have. So this can be implemented efficiently in a recursive manner. All right, so let me give you one example, like a practical example of how this works. And let's go back to the problem of ocean acidification. So the problem there is that we have increased CO2 emissions. They affect a quantity called the aragonite saturation, which in turn affects the capacity of marine organisms to build their shells in coastal regions. And there is actually a high risk that, I don't know in how many years, but we might not be able to enjoy all the oysters and the lobsters that the New England fisheries produce because of this effect. So now we have a project at MIT where we propose to build a cost-effective monitor mechanism. And the cost comes in this way. The quantities of interest that quantify the effect of ocean acidification are very hard and very expensive to measure in practice. So for example, here, the aragonite saturation, one has to go out in the ocean, collect samples, bring them back to the lab, and analyze them just to get a measurement for the aragonite saturation. And we need a lot of measures in space and time in order to make a predictive model. So what we propose is to use this multi-fidelity framework to utilize different information sources. We could have chip sensors, we could have some oceanographic computer simulations, and towards the top of the pyramid, we could have some high-fidelity measurements. And what we're trying to do is we're trying to use auxiliary quantities that are correlated to this aragonite saturation to predict this variable that is hard to measure. So we know, for example, that this could be correlated to pH or total alkalinity or temperature, which are easier to measure. So we're trying to build a framework that we can mainly train and learn from measurements of pH and temperature, and eventually being able to predict the quantity that we're interested in. And this is just a small demo that we're trying to reconstruct the temperature throughout the year 2013 in the Gulf of Maine, using some cruise data, and the lines that you see appearing are some trajectories of cruises that traveled and made some temperature measurements throughout these months, and also some low fidelity and noisy satellite data. And here you see the prediction that we get in degrees Celsius and the associated uncertainty. So this uncertainty later on can guide you in, say for example, you can afford a new measurement, you can adaptively place, you can choose the location of a new sensor and so forth. So the probabilistic nature of these regression models allows you down the road to perform adaptivity. What is tricky here is that the model that I just used, the autoregressive model of Kennedy and O'Hagan, works really well when the information sources are well correlated. They exhibit a very nice, clean, and strong linear correlation. For example, something like here, right? But in many cases, different variables, this is like an idealized setting, right? In many cases, you have data like that. Salinity correlates with DIC like that, or different, like chlorophyll is another quantity of interest, correlates with this variable in a very complex manner. So, as I said, our goal is to infer the ocean acidification metrics are hard and expensive to measure. We want to infer them from observing auxiliary quantities that are available. So we need to come up with a framework that is robust and can learn from, and can distill information from these complex cross-correlations. So I'll show you an extension that we made to this Kennedy and O'Hagan framework. So starting from this point, and let's assume we just have two information sources to keep things simple. So we're generalizing this scheme. So this representation that F2 is rho times F1 plus delta 2 to this expression. F2 equals another nonlinear function of x and F1. And this is kind of, for you working in deep learning, this is exactly the setup. We have a nested composition of nonlinear maps to capture the relation between F1 and F2. So we're generalizing Kennedy-Hagen's model to this nonlinear expression, and now we put a Gaussian process prior on the lower fidelity model as before, but also a Gaussian process on G2. And that makes this model what people are calling a deep Gaussian process. So F2 is no more a Gaussian process. So a Gaussian of a Gaussian is not a Gaussian. This makes inference way more complicated, but under some assumptions, again, we were able to come up with a recursive scheme that does not cost any more than a standard Gaussian process regression, albeit it's embedded in a higher dimensional space. So again, if F1 and F2 is d-dimensional, let's say, the inputs are d-dimensional, this prior is d plus 1 dimensional. So we're augmenting our function to a d plus 1 dimension. And I'll show you how that helps down the road. And then down the line, this construction, it just gives us, it's also very easy to implement, it just gives us a very particular structure for the prior. So once we choose the covariance function, so this is again an admissible prior because multiplications and additions of admissible covariance kernels give you another admissible covariance. All right, so let me show you a very deceptive but simple example to illustrate how this works. So assume we have two information sources. A low fidelity model is just a sine wave, and the high fidelity model is just the same sine wave, but with a quadratic nonlinearity and a non-uniform scaling in 1D, right? So here I'm plotting the low fidelity model, which is the red curve. The high fidelity model is the blue curve. And now I'm also plotting the observations. We do not know the function, we just have data, right? So we have black crosses for high fidelity data and red circles for low fidelity data. And as you see here, the low fidelity model, every other period is pointing to the wrong direction, right? And that's a case that we expect. When we're modeling something with a low fidelity, a simplified model, the low fidelity model is only valid at a very particular range of parameters, right? We cannot expect it to give good results everywhere. And that's exactly the case here. Every other period, the low fidelity is totally wrong. All right, so if I plot here low versus high fidelity, we get this very complicated cross-correlation. It's not even functional. This is not a function. So the model of Kennedy-Hagen that works very well with linear cross-correlations will totally fail. All right, let's start now by just fitting a Gaussian process model to the high fidelity data. Assume that's the only thing we have. So this is what we get. This is the exact high fidelity function we're trying to approximate. And the red dashed line is the mean of the Gaussian process posterior, and the shaded region is the variance. So because the function is severely undersampled, we cannot really get any meaningful prediction. Then we go to do multi-fidelity on this data using the Kennedy-Hagen model. The problem there is that that model cannot learn this complex cross-correlation. It's going to learn a scaling parameter rho. If you remember, it's going to set that to 0 because it cannot find any information there. And pretty much the prediction you obtain is of similar nature and quality to just doing single fidelity Gaussian processes. Versus with this new nonlinear scheme, we are able to recover from very few data to recover this complex cross-correlation and reconstruct the high fidelity signal with high accuracy. So, and the way this works, I have a plot just to demystify because it may look like magic. So the way it works, as I said, we're embedding this problem into a higher dimension. This is a one-dimensional function. Essentially what we're doing here, we're learning this latent two-dimensional manifold. So, and what this helps us do is really to disentangle this complex nonlinear cross-correlation. So if you see this magenta line here, it's just the projection of this cross-correlation on this manifold. And this becomes a simple and a nice, smooth curve that we can learn. So effectively, how this learns, from the joint low and high fidelity data, we learn the manifold, and then we can go from low to high fidelity by just projecting the low fidelity data up to the manifold, and then there's a simple function, smooth function, that takes you from the manifold to the high fidelity domain. And this is exactly what happened with this example, just to demystify how the method works. All right, so this is in a nutshell, some of the capabilities of multi-fidelity modeling. Now I'm going to take it one step further and show you how we can use the probabilistic nature of the surrogate models to efficiently solve optimization problems. So, and that leads us to the concept of multi-fidelity Bayesian optimization. So our setup is the following. We want to identify a set of parameters that generates a response matching a target performance Y star. Or, yeah, just solve an optimization problem of this form. For example, this could be a parameter calibration problem, right? We have F, which is a black box and expensive to evaluate objective function. So to get just for a given input, to evaluate F, we might have to spend a few days on a supercomputer. F could also return noisy observations, so it could be experimental data. And we have no gradient information available for F. So, all right. So our approach, again, we take a Bayesian approach. We're going to place a prior on F. We can construct a multi-fidelity, a nonlinear multi-fidelity surrogate for F. And then we want to use the posterior distribution we have. And this is, for example, just an example where we're trying to maximize this 1D function, right? This is the Gaussian process. We have the posterior variance. We can use this posterior variance to design an efficient sampling plan, to choose where we're going to put the next point towards efficiently identifying the maximum. So to this point, we have to introduce the concept of an acquisition function, which is like a proxy function that takes information out of this posterior, and then it tries to balance what is called the exploration versus exploitation trade-off. In other words, it will tell you to go sample somewhere in the space so that you reduce your uncertainty in that region of the space, which is exploration, versus exploitation is going to go sample where you think that the minimum or maximum is likely to reside. It has a good probability of being there. And so this defines an iterative process. So we're transforming this problem into optimizing essentially the acquisition function. So in this iteration, we have this data. This is the posterior. This is the acquisition function we created. And we're going to go place our next sampling point wherever this acquisition function is maximized. And then we're going to go gather the new observation, update our Gaussian process model. We have a new acquisition function, find where it's maximized. And typically, this is cheap to evaluate, and we have gradients available for this. All right. And there comes the modeling choice of choosing the appropriate acquisition function. So this is an open question, and it's an open field of research on how to set up efficient acquisition functions. All right, let's go through this concept through a simple example. All right, going back to the blood flow simulations, we want to calibrate this idealized carotid bifurcation. We want to calibrate the outflow boundary conditions where we just attach some electrical analogs that they model the downstream dynamics that we neglect in this truncated domain. So we want to calibrate those resistances such that the pressure at the inlet of the domain matches some target value. So if you formulate it as an optimization, we want to find X star. So X star, X is a vector of those resistances that minimizes this discrepancy for the pressure at the inlet. All right. And we want to use multi-fidelity here because solving this optimization problem using 3D Navier-Stokes, every time, at every iteration of the optimization, you have to solve a high-fidelity simulation, which takes order of hours to perform. So here we're going to employ some lower fidelity models, namely a nonlinear one-dimensional fluid structure interaction solver that we can evaluate in order of minutes. And we're going to also employ a linearized version of the solver, which we intentionally linearize around the inaccurate reference state so that this is a really low fidelity model. And we can evaluate at order of seconds. So our goal here is to identify the optimal values of the resistances at minimum cost. We do not want to be evaluating the high fidelity model too many times. All right. So this is in 2D, just assuming those two resistances, I can actually, for this simple problem, I can actually plot how this objective function looks like. So these are the values of the resistances at the outlets. And now using 250 Navier-Stokes simulations, we have a response surface like that. And this is the discrepancy of the pressure at the inlet. So this is kind of like the function we're trying to minimize. But for this problem, we have it because it's easy, but generally this will not be available, right? All right, so this is what we get by the multi-fidelity framework. Um, so we initialize the algorithm. So we sample only once the high fidelity solver. We sample the low fidelity solver about 50 times. The intermediate fidelity about like 10 or 15 times, and we get an initial response surface. Now we're gonna go evaluate, we're gonna interrogate the posterior distribution we have. We're gonna evaluate the corresponding acquisition function, and here I'm using a criteria called the expected improvement. And we're gonna go place our new point wherever this expected improvement is maximized. So then if we repeat this iterative process, we can actually find the minimum of this function with only 3 iterations, like 3 evaluations of the highest fidelity model, mainly relying on low fidelity information. Here I'm plotting the points. These are the linear solver points where they're very inaccurate, but they do capture a useful trend. And then the red dots are the intermediate fidelity, and we only have 3 evaluations of the expensive Navier-Stokes solver. And this plot here is just the uncertainty of the Gaussian process predictor after those 3 iterations, and you see that it is pretty certain about the function it's approximating. So the variance is bounded by 10 to the minus 4. So it's kind of like reassures you that you have a good quality response surface. All right, this was one example. Now we're going to show you another example in design. So this is a DARPA project that we've been working on at MIT, and our goal is to optimize structural components of this futuristic naval vessel that it's supposed to reach speeds of 120 knots. This is like twice as much as anything out there. So quite futuristic. And one part of the project is to, in full speed, this vessel is actually flying out of the water. It's only those hydrofoils. I don't know if you watched the latest edition of America's Cup in Sailing. This is the same concept. And the main problem there, from a physical point of view, is a phenomenon called cavitation. In very high speeds, you have the fluid is chasing phase. So you have pockets of vapor developing on the faces of those hydrofoils. So the challenge there is to optimize the shape of this hydrofoil so you operate in a super-cavitating regime. So in other words, you have a stable pocket of vapor formed around your hydrofoil, and essentially that reduces dramatically the drag resistance, the friction resistance, and allows you to reach these crazy speeds. All right, so using the concept of multi-fidelity Bayesian optimization, we can set up a loop where we only need the human expert to do 2 things for us. One thing is to give us a good compact parameterization of the shape of the hydrofoils. And the other thing is to give us a range of admissible values for the parameters we're trying to optimize. So once we have this setup, we can employ like a simulation-based approach, and we have variable fidelity solvers. For example, we can do 2D simulations on different cross-sections of the hydrofoil. We can account empirically for 3D effects by combining those 2D simulations with some theoretical formulas on the spanwise direction that do some empirical corrections called the lifting line theory. We could do full-blown 3D simulations, and these are all challenge simulations. These are turbulent multi-phase flow simulations, so there are a lot of uncertainties in the modeling there. We can also incorporate some experimental data that we have from experiments in cavitation tunnels. So the goal is to combine this information to perform this information fusion using probabilistic surrogates, then interrogate the posterior distribution of the surrogates through Bayesian optimization to choose the next sampling point, and go through the loop till we have some acceptable result. And this is pretty much the workflow here, right? So we have an initial sampling plan where we evaluate our models, we construct surrogates, we choose an appropriate acquisition function, we optimize the acquisition, we choose the next point, and then we check for convergence. So convergence is, for example, if you're using the expected improvement, if the algorithm tells you that there's not much improvement to make, if you acquire one more point, maybe that's a time to stop. Or if you see that you've reached a plateau and things are not improving much, you can stop there. And this is just an illustration of how this works. So the setup is the following. We want to minimize this quantity of interest 1, which is just the drag over lift ratio of the hydrofoil, subject to some constraints. So we have a constraint on the performance. We have a constraint on the thickness of the bubble, which is another variable. We have some structural constraints on the inertia of the profile, of the hydrofoil profile. And this is how kind of like this convergence looks. We start from a benchmark design that we compare against, and this design was the best that the naval architect could come up with, using his experience and also using some genetic algorithms to optimize using the lowest fidelity model. So he used simple potential flow simulations through a genetic algorithm, and after about 50,000 evaluations, he was able to come up with this optimized design. So this was our starting point. So using this Bayesian optimization framework, this is the iteration number. As you see, what happens is, okay, in the beginning we had a nice drop, and then things do not change a lot. And here I'm plotting the distance the distance between two consecutive designs. So it's designed here, it's 2D profile, it's parameterized by 15 variables. So this is this L2 distance in this 15-dimensional space. And what shows is that the algorithm, when the distance jumps, it goes and explores some different region of the design space to see if there's anything useful there and to reduce the uncertainty. And when it concentrates, this distance is 0, it means that it's focusing on a particular region of the design space because it thinks there's a good design there. And this is exactly what you see here. So you get a good design, and then you explore a bit, you're not able to come up with something better, and then suddenly, once you investigate a sweet spot of the design space, you get further improvements in the performance. So now we got, for this case, I think we got an improvement over the already optimized design of about 10 to 12% by just performing 735 low-fidelity simulations and 120 high-fidelity runs, which is orders of magnitude. First of all, this framework enables you to use the high-fidelity simulations, while the genetic algorithms, you cannot really afford 50,000 multi-phase, turbulent Navier stochastic. All right. So these are all some good results so far, but let me show you some drawbacks and limitations of this framework. All right. So one we already mentioned, Gaussian process surrogates suffer from a cubic scaling of the data, but there are effective ways of addressing this in practice. You could come up with low-rank approximation to the covariance matrix and or like sparsify it, so you can use sparse linear algebra to invert it. For stationary priors, you can transform the learning process into the frequency domain. So instead of performing maximum likelihood estimation, you can use FFTs, and essentially this allows you to scale linearly with a number of data. Or you can use some approaches that are very popular these days in machine learning, for instance, stochastic variational inference, which allows you to train your model by just taking mini batches, like subsamples of your full data set, and do stochastic gradient descent and update the model parameters sequentially like that. Another limitation is that Gaussian processes are great priors over smooth functions. If your response has irregularities, if it's heavily non-stationary, and stationary, I mean stationarity in space. So the autocorrelation is a function of space. So in this case, a simple Gaussian process prior would have a horrible time approximating your function. But there are ways around it by just using warping layers. And this is just a standard thing in deep learning where we're gonna map the input space to some hidden space through a nonlinear mapping that we're learning. And then we hope that from this hidden space to the actual data, it's a simple smooth function that governs the relation. So you could have, if now F1, so F2 will be a Gaussian process. If F1 is some parameterized function, like a log or a sigmoid, people call this warped Gaussian process. If this is a neural network, this is called manifold Gaussian process. Or if this is a Gaussian process itself, this is deep Gaussian processes, which is like the probabilistic Bayesian equivalence of deep neural networks. All right, and another limitation is scaling to high dimensions, because if you use a tensor product prior, then that requires exponentially many training points in high dimensions. So you will have like the curse of dimensionality biting you back. But there are some ways to deal with that, and here I'm highlighting a recent paper with my colleague Daniele Venturi and George Karniadakis, where we combine this frequency domain learning and this data-driven kernel approach to effectively address the high dimensionality and the big data issue. I'm not going to talk much about that, but I have some backup slides. So if you're interested, we can take it later. All right, so we talked about multi-fidelity modeling and Bayesian optimization. Now I'm going to show you something that was a byproduct of these developments. So some work I did with a colleague of mine, Mazia Raisi at Brown University, where one of those late night eureka moments to say, okay, we can use this Gaussian processes framework to solve differential equations. All right. So in particular, linear differential equations. That is where the general statement that we can make. So you have a linear operator acting on an unknown solution, and then you have a right-hand side. And these are just different examples of equations that we solve. So you could have an integral differential operator. This is a 10-dimensional Poisson equation. This is a time-dependent problem, advection diffusion reaction. And this is a fractional operator. For those of you who are not familiar, these are like non-local problems that can model anomalous transport, anomalous diffusion. So it's not the standard integer order derivative that we're used to, but this operator allows to take a derivative of order 0.78 of a function, which is not local and non-local anymore. So you have to take into account memory effects here. All right, so the main idea here is, again, we're not going to represent our solution in terms of a basis, as we do typically in numerical analysis, but we're going to put a Gaussian process prior on the unknown solution. Then because of linearity, the right-hand side has a Gaussian process prior, and the kernel K has a very particular structure. So the kernel K is related to the kernel G through this operation that carries the structure of the linear operator. So now our problem setup is the following. We assume that F2, the forcing, is an unknown black box function. We could have like multi-fidelity there, like a collection of multiple information sources and so forth. We only have access to scattered, noisy, and variable fidelity information of F2. And we have no data on U2 whatsoever other than perhaps the boundary conditions that make the problem well posed, or in many cases, we don't even need boundary conditions. We could have measurements of the solution inside the domain. So these type of methods, because it's just a regression problem, it only sees data. It's not really aware of, doesn't care much about specifying boundary conditions. And we're going to do this by just solving a regression problem, so non-numerical discretization is involved. So it's really interesting, and there's this emergent wave these days of a field called probabilistic numerics, that they're trying to revisit numerical methods from a statistical inference perspective. And what is really interesting is that this traces all the way back to Perdikaris courses on probability theory. And there was Percy Diaconis from Stanford that picked it up in the mid-'80s, and he wrote a very nice paper on Bayesian numerical analysis. And this is a very nice quote that he mentions there. So once we accept that we don't know F, but we do know something, we have some prior information, it becomes natural to take a Bayesian approach. And this is another endorsement by David Mumford. In a report he wrote in 2000, he said, the stochastic methods will transform pure and applied math in the beginning of the third millennium, as probability and statistics will come to be viewed as the natural tools to use in mathematical as well as scientific modeling. All right. So let me give you just a motivation, kind of like an application of how this particular framework can be used in a kind of realistic problem. So assume you want to estimate the deflection of a wing subject to the flow around it, right? All right, and assume that this deflection is governed by the laws of linear elasticity. So you can write down the equations of linear elasticity, and you have a forcing term that comes from the surrounding flow that causes the deformation. So this is just a one-way coupling. If someone gave you the flow field, and you just want to compute how the wing is going to deform. And now the sources you could have for this forcing term could be multi-fidelity, right? So for example, you could have sensors measuring pressure on the wing. So you have noisy sensor data that you trust, and they're high fidelity. You could do large eddy simulations around the wing and compute the pressure field and get those forces from simulations. Or you could do some very crude and cheap but inaccurate potential flow simulations at the lowest fidelity model. And now the questions we want to ask is like, okay, how can we combine all this data that's available to accurately estimate the wing displacements under the laws of linear elasticity? So this blends to what I just said. We have a linear equation, LU equals F. And data on F comes from all these different sources. The second thing we can ask is, what is the uncertainty or error associated with this estimation? And then how can we best improve the estimation if we can afford more measurements? So if someone says, okay, I can place one more sensor on the wing, where should I go put it to maximize my information gain and learn more about the displacement? All right. So This is kind of like putting in the context of an application, but here I have like a toy problem just to demonstrate how things work. So here on the left, you see just the Bayesian workflow. We have a prior, we have data, and then we obtain a posterior. So this is what I just said. U has a GP prior, this is the equation, and through the equation, the right-hand side, F, has a particular Gaussian process prior with this structure. Now we get to observe data. And now in this column, I have a single fidelity data example. In this column, I have a multi-fidelity. So let's start with a single fidelity. What we only know is measurements of the forcing at those 3 points. This is the exact force function that generated it, but it's black box. We assume we don't know. I'm just plotting it just for illustration reasons. So what we know in this example is those 3 data points on the forcing. And then we also have 1 point on the solution, which we call anchor points just to distinguish them from the classical boundary conditions. All right, so given those 4 training data, we can solve the Gaussian process regression problem, and then we can obtain a posterior on the solution of the equation, and this is the prediction of the posterior mean, and this is the variance associated with this prediction. So you get like a posteriori error estimate on your prediction here. So same example here, if I inject some more low fidelity data, noisy low fidelity data on the forcing, and now retrain using the multi-fidelity framework, you get this updated answer for the solution to the equation with an uncertainty band. And there is no discretization of the equation whatsoever. So this is 1D example for this integral differential equation, but we have like an archive paper that's under review now where we have time-dependent problems and higher dimensional equations, and even the fractional equation that I showed you before. So now the cool thing is having this probabilistic posterior, we can interrogate and do things like active learning, like adaptive refinement to do that. So this is a 2D Poisson equation. Here I'm plotting the uncertainty on the predicted solution. And these are the training data points on the forcing. So these red dots are the collected data we have on the forcing. We also have data on the boundaries because we know the boundary conditions. We want like 0 Dirichlet boundary conditions for this problem. All right, so this is the uncertainty associated with our predictions, and this is the pointwise error for this particular case, which we know we fabricated an exact solution and we can measure the error. And one thing you can notice is that in many cases, as we'll start iterating this active learning scheme, the posterior uncertainty is a good a posteriori estimate for the pointwise error. All right, and the panel here, I have the uncertainty of the right-hand side and also the pointwise error. And here I'm coloring with a different color coding because this uncertainty is gonna guide the selection of the new sampling point. We're gonna place a new point where this is maximized. So red dots denotes the training data actively collected by the scheme. Star denotes the next sampling point suggested by the scheme. And here I'm plotting convergence, relative error for the solution and the forcing, as we start acquiring new data. All right, so some interesting things that you will see here. First of all, the convergence is not monotonic, right? What we're used in spectral methods, we see this very fast and highly accurate convergence rate. So here what happens is that the algorithm explores. As soon as it has gained enough information, then it becomes more accurate. Then it stalls a bit, explores, and then it becomes more accurate. And this is a very naive criteria for data acquisition. That's the simplest thing we could come up with. Another thing that you're going to observe is now, throughout all these iterations, the error in the solution is bounded by the error of the forcing, and this is going to change somewhere here because of errors introduced at the boundary. So we have collocated the boundary condition on a finite set of points, and in order to keep getting a better solution, we need to add more points at the boundary, and this happens somewhere around here. So this is kind of like an active learning scheme. And as you see, it ends up having this staggered grid, right? It's not like this equispaced sampling grid. All right. Then in this case, our goal was to learn about the solution of the problem globally throughout everywhere in this square domain, right? But in many cases, one may only be interested in a maximum response. Say, I want to identify only the global maximum or the global minimum of this. So we can couple this problem with the concept of Bayesian optimization, and this is just another toy example to highlight this. So here we want to estimate probabilities of failure in linear elasticity. We have this idealized Euler-Bernoulli beam that's governed by this fourth order equation. So we can collect data on the forcing only, noisy data, and our goal is to identify the maximum displacement of the beam given these boundary conditions. So given noise observations of the loading, solve for the displacement, find the maximum displacement, and given a given threshold, this line, this dashed blue line, find the probability that our solution exceeds this threshold. And this is what I'm plotting. So this is our solution after we have acquired only 1 point on the forcing. So this 1 point on the forcing, this is the exact forcing, the blue line. This is the exact solution, which we don't know. This is the Gaussian process, approximate the forcing, which is completely wrong because we just only have one observation. And I'm gonna play the movie, and you will see as we start acquiring new data points here, the algorithm is gonna focus on identifying the minimum down here. And here I'm plotting the acquisition strategy we're using, which is what people are calling a lower and upper confidence bound. This is the way we post-process the posterior to get a new sampling point. So as the movie goes on, you will notice that more points are collected on the forcing, the posteriors are updated, and then at some point we're gonna be focusing where the minimum is. And with few function evaluations, you pin down exactly where the minimum is. You don't care much about what happens far away from it. You just focus here. And this is the probability of failure, the probability of exceeding a threshold. So all these x's here have a displacement larger than the threshold we specified. All right. Okay, this is all great, but it just holds for linear equations, right? And so it's great, but I'm not sure how useful it is. So how can we, and the problem with nonlinear equations comes here, right? It violates this point. Oops. So use linearity to get a prior on the forcing. If your equation is nonlinear, then a nonlinear transformation of a Gaussian process is not gonna be Gaussian anymore. But what we can do is to introduce some time-stepping scheme. So now, the choice of the equation, along with the choice of a time-stepping scheme, will define a new Gaussian process prior. And take, for example, this one-dimensional Berger's equation. So we have the equation with some boundary and initial conditions, and then, oops, I think I skipped one slide. Yeah, let's start from here. All right. So we're gonna discretize this equation in time using our favorite time-stepping scheme. Here, for example, I'm using backward Euler. And we're gonna treat the nonlinear term semi-implicitly in time. So that will become, we'll take un from the previous time step and un plus 1 from the current time step. By doing so, this becomes, so un plus 1 and un are related through this linear operator now because of the semi-implicit treatment. So we can apply the same machinery, but now at every time step, right? So we're gonna start with the Gaussian process prior at time step n plus 1. We have a Gaussian process prior for time n with this very special kernel that sees this Berger's equation discretized by this backward Euler scheme. And at every time step, we're gonna do our inference exactly the same as before and solve the problem in time. Now the catch is here that at every time step, we're gonna generate new data to be the forcing for the next time step. So this data is artificially generated by the model. So we need to take care of how uncertainty is propagated. And we have like an upcoming paper in this, and we can talk about it. It's a technical part. How do you properly propagate uncertainty in time? All right. So this is what happens in this particular Berger's equation. We have chosen the viscosity to be of this particular value because we know that the solution develops a shock. And these are some really cool remarks. So despite the fact that we're starting from a very simple and stationary prior, the structure of this kernel, because it sees the Berger's operator, it can generate paths that have the discontinuity. That is one observation. Another observation is that this is a general approach. Just take a nonlinear equation, choose your favorite time-stepping scheme, and this framework can apply on that. And the only catch here is that you have to be able to apply the nonlinear operator or like the discretized linear operator on a starting kernel. So but Mathematica in most cases can do the symbolic calculations for you. And another thing, under this setup, we can use fully implicit time-stepping schemes at no cost. It's exactly the same thing as using an explicit or an implicit time-stepping. But by using implicit time-stepping, we can get stable schemes. We can afford accurate and stable schemes with large time steps. So that is one perk of this approach. And these are just, this is a plot for the Berger's equation. So only thing we see is initial noisy data. So this is the equation. We have initial condition on the solution, and the x's are the observations that the algorithm sees, which are corrupted by noise. And we have boundary conditions, Dirichlet boundary conditions at the ends of the domain in time. So this is the solution after some time, posterior mean and posterior variance, solution after some time, and you see, the shock develops, and we're still able to capture it quite nicely. And also quantify the uncertainty. So this uncertainty comes due to the noise in the initial data and due to any subsampling we're doing in the process of time stepping. So it quantifies those two errors. All right, so I have another example, which is to advocate how using implicit time stepping gives you cool results. So this is an example for a long-time integration of a linear advection equation. There's a linear equation. We take a sine wave, and we advect it with periodic boundary conditions for 50 periods through the domain. And then we take a classic scheme by Peter Lachs, the Lachs-Wendroff scheme, which is a second-order scheme. And you see that after 50 periods of this advection, you have dispersion and diffusion errors that totally kill you. So now with the magenta line, I'm using the proposed framework using an implicit Runge-Kutta fourth-order time stepping. And you see that, with a time step of 10 to the minus 2, after 50 periods, you're still following the solution quite nicely. And this is just the convergence as time, the L2 error as time goes on for the two different schemes. All right, so same example for a wave equation. Here we start from the left panel, we start from noiseless initial data. On the right panel, we start from noisy initial data, just to show you how the uncertainty is propagated, and you can keep track of it. So maybe to see the data. So this is where we start from. This is a noisy, it is a noise-free initial condition, and this is a noisy initial condition. And then we just march using implicit Runge-Kutta second order, I think, in this case. All right. So for people that do uncertainty quantification, the way I like to think about it is you have an input, which is the noisy data, which is a infinitely many correlated Gaussian random variables, because that's how we approximate it with the Gaussian process. And you propagate this infinite dimensional process through your equation in time, and you quantify the uncertainty in time. All right. Okay, so just to summarize, I introduced the concept of multi-fidelity modeling, the concept of Bayesian optimization, and showed some applications on design and inverse problems. Then this is a new exciting development that this is kind of machine learning meeting scientific computing, classical scientific computing. So we're using the equations themselves to construct priors to do statistical inference. And I think this is like an open field, which is quite exciting to blend those two. All right, and then kind of like a vision for future research, which is kind of like general. So we talked about multi-fidelity models. We have on the modeling and computation front, we have high order methods, fast solvers. There's huge efforts on coupling, multi-physics solvers. Then you have applications which are driven by real data, like experimental data. Of course, you want to have you want to inform the policy and decision-making. You want to produce results that inform policy decision-making. Those two are connected by high-performance computing. And then there's a new player in the game, from my point of view, that is statistical learning, that allows you to synergistically combine experiments with simulations. It allows you to come up with meaningful representations of your data. It allows for hierarchy and compositionality in the way you construct surrogate models. It's a natural setting to quantify uncertainty in the predictions, but you can also combine this with our modeling knowledge to construct proper prior distributions and inform the statistical schemes using prior knowledge. All right. So I think that's all I have for today, and I'll be really happy to take any questions.
Thanks very much.
Yeah. Right. So we're using this recursive scheme. So the inference is done, you do a regression problem at the low fidelity, then you take the posterior of that, you plug in the higher fidelity. So you can actually compute acquisition functions for active learning or Bayesian optimization at each level of fidelity separately, and then just sample each model according to that. That does not see the correlation between the models. It's not the best way of doing it. But so far, that's how we have dealt with it. Ideally, you want to come up with an objective function that globally sees all the cross correlations between the models and optimize that. But it's a little bit tricky, more tricky to do that. Yeah, so at each level, yeah, I sample each level independently from the other. Correct, yeah.
So assuming that you have that kernel,
yeah.
If that's a hard problem, then
yeah, but for the most cases, you have it in closed form. I mean, or you can evaluate. It doesn't have to be in closed form. So let's see here. For example, if you're dealing with non-stationary problems, right, and you're taking this approach, maybe you put a neural network on a fund. This will define a very complex kernel that comes out of the neural network. You don't have it in closed form, but you can evaluate numerically. You can do back propagation through the neural network to fit the parameters. So it's not like a necessary requirement to have an analytical form of that. It makes things simpler, for sure. Like.
How different is this from Kriging?
Yeah, Kriging is exactly the same thing, but the training step is different. Here we use the likelihood. I mean, Kriging is the fitting of, in Kriging, the way they fit parameters is kind of like using these empirical variograms and so forth. This is a principled way of doing learning using the maximum likelihood, the likelihood of the model. So this is the only difference between what people are calling Gaussian processes for regression and what people are calling Kriging geostatistics. And this treatment enables you, it makes things a lot easier when you're dealing with, then again, with multi-fidelity and multiple correlated outputs. And, yeah, exactly. Yeah. Yeah. It's only the training step that is different between Kriging and the Gaussian process community, the way they deal with that. Yeah. So, you mean, well, we've done the inviscid case as well. I didn't show results, but the same thing holds, the same framework works. I also have results for the inviscid case. Yeah. No, actually the viscosity, let's see. We actually do have a shock in this case, so it's very close to in the inviscid limit, right? Or maybe, or is it, maybe I made a mistake here. Maybe it's a typo on the value of nu. Yeah, you're right. Yeah. No, nu was the order of 10 to the minus 2 or 10 to the minus 3 here. Yeah, so it's a typo. Yeah.
So one of the things that sort of seems to be
Mm-hmm.
I talk to people about this and go, well, we can go to the training set, so we're fine.
Yeah.
And so that's the great answer. One of your training set is really
Yeah.
So what happens in situations, if you're thinking about many of the situations that we want to work in, we might have situations in which we really want to go some distance from that into a much more general.
Yeah, so one distinction here between neural networks and this. So neural networks are parametric models. This is a non-parametric in the sense that, okay, it enjoys all the properties of Bayesian non-parametric models. So it's immune to overfitting. That's one thing because of the Bayesian formalism. Another thing, you do get this posterior uncertainty, right? That kind of quantifies the error. The catch here is that depends on your prior, right? We can hide it under the carpet, but it does depend on your prior. So different priors will give you different uncertainty estimates. And choosing the prior is where the human expert comes in, and it's problem dependent. Yeah. Sure. Yeah. You could.